The Power Spectrum of a Random Walk by Colin Scheibner. A project at St. Olaf College for Physics 374 taught by Dr. Amy Kolan.
A random walk? What is that?
Consider the following example. Suppose I have a pet ladybug which I have trained extremely well to perform the following trick. The ladybug starts at the origin, and every second I flip a coin. If the coin reads heads, the ladybug takes one step in the positive direction. If the coin reads tails, the ladybug takes one step in the negative direction. If we plot the position as a function of time, the resulting curve is an example of a random walk. The essential feature is the effectively random decision between a positive and negative displacement at each time step. Using Mathematica, I will create 3 examples of random walks, each 10,000 steps long. I now plot the 3 random walks as functions of time. If we think of adjectives to describe these graphs, we might think of dissimilar or unpredictable. Yet over long periods of time, you might notice that there is a certain amount of rhythm or predictability. For example, within 10,000 steps, each of these plots returns to the 0 position multiple times. We can make these qualitative observations more mathematically precise by taking the power spectrum of these walks. Looking at the power spectrum for the blue random walk, we see that high amplitudes are associated with low frequencies. This reinforces our visual intuition that random walks exhibit some degree of predictability and repetition over longer periods of time. The relationship between amplitude and frequency is made explicit when we plot the power spectrum on a log-to-log scale. We notice that the power spectrum for the blue random walk is clearly linear on a log-to-log scale. Moreover, the power spectrums for the green, red, and blue random walks are nearly indistinguishable. The linear relationship on the log-to-log plot indicates an exponential relationship between frequency and amplitude. By finding the slope of the line of best fit, we find the degree of exponentiation between frequency and amplitude. We discover that this slope is -2. Which leads us to our conjecture that the power spectrum of a random walk goes as 1 over frequency squared. We state this claim formally here. In this notation, the p with the square brackets around x indicates the power spectrum of x. We use omega to denote frequency. We will show that the power spectrum of a random walk decreases as 1 over frequency squared. The proof relies on 3 key ideas which I will develop subsequently. That the derivative of a random walk is white noise, that white noise has a constant power spectrum, and that the Fourier transformation, in some sense, turns calculus into algebra. If we recall the example of a random walk presented at the beginning of the video, it is clear that its derivative is simply going to be a random sequence of positive and negative ones. In fact, this is the defining feature of a random walk. Often, a random walk is referred to as brown noise or a brown signal, and its derivative, which is a completely random signal, is called white noise. Let's consider the power spectrum of this white noise. Suppose this power spectrum is non-constant and has a peak somewhere. This implies the existence of a favored frequency at which the signal tends to approximately repeat itself. However, that completely contradicts the idea that the white noise signal should be completely random. Using this heuristic, we can intuitively understand why the power spectrum of a white noise signal is constant. In fact, a constant power spectrum is often taken as the definition of white noise. Now we demonstrate a convenient mathematical relationship between the power spectrum of a function and its derivative. If f is any real-valued function of time, recall that the power spectrum of f is simply defined as the amplitude squared of the Fourier transformation of f. Using integration by parts, we can relate the Fourier transformation of the derivative of f to the Fourier transformation of f itself. Taking the amplitude squared of both sides of the preceding equality yields an intriguing relationship. Essentially, taking a derivative inside the square brackets is the same thing as multiplying the entire power spectrum by omega squared. Let's see this relationship pictorially. If f and f prime are real-valued functions of time, we can choose to identify them either by their representations as real functions or by their respective power spectrums. In real function space, if one wishes to get from f to f prime, one simply has to take a derivative. However, in power spectrum space, to get from the power spectrum of f to the power spectrum of f prime, one simply needs to multiply by omega squared. This is due to the behind-the-scenes work of the Fourier transformation we did on the last slide. This is why we said that the Fourier transformation turns a relationship defined by calculus into a relationship defined by algebra. We're ready to put the entire argument back together. If x is our random walk, then we know that the derivative of x must be white noise. But as we discussed, the power spectrum of white noise is constant. Lastly, we discussed a convenient relationship between the power spectrum of a function and the power spectrum of its derivative. Combining these three facts yields our desired result. Now that wasn't so bad after all. Let's draw some conclusions about random walks. We showed that a random walk is simply the result of randomly choosing between positive and negative displacements over a sequence of time steps. After examining several examples, we noticed an astonishing feature. Despite the unpredictability of the random walks, they all shared the same 1 over omega squared form in their power spectrums. Lastly, we provided an intuitive mathematical proof to explain this phenomenon. Random walks are one of the elementary mathematical tools of statistical mechanics. A typical application is to use a random walk to model the motion of a particle under diffusion. Now that I've talked the talk, you'll be ready to rock the walk.